All right, we're going to start talking about the energy chapter, which is on PowerPoint 5, energy. Energy is simply the ability to get things moving. It's the easiest way I can think of it. So these glasses here, place it on this table here. They have some sort of energy associated with them. And you might think, well, why is that? Well, it actually has the ability to move down. It has the ability to drop off of this particular desk right here. Because it has the ability to do that, we say it has some energy associated with it compared to these glasses if they'd be on the floor. And energy is measured in certain units. So let's talk about the units of energy. The units of energy, it's going to be measured in units that we call joules. There's also another unit of energy that we use that's called the calorie. And this gets a bit confusing. You're familiar with the term calorie probably with the food that you eat. Well, there's a problem there because the dietitians, the calorie that dietitians use is actually a kilocalorie. So if you're carefully looking at, say, the package of food that you eat, you'll notice that the calorie in the food that you eat is always written with a capital C. So I'm going to write it like that, a really big C. So 1 food calorie is going to be equal to 1,000 little c calories. I know, it's goofy. It's just the way that is. So a food calorie is actually a kilocalorie, equals 1 kilocalorie. And that's an important distinction to remember. The calorie, the little c calorie, that's going to be, there's a way to define that kind of makes sense to people. 1 little c calorie, it's not that much energy. It's the amount of energy. I abbreviate energy with 3 letters, N, R, and G, because if you say them real fast, energy, it sounds like energy. So 1 calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So that's it. It's really not that much energy. And we're going to, again, need to recognize that it takes 1,000 of these little c calories that are defined like this to equal 1 food calorie that you're used to. And there's also a second relationship that I want you to know. 4.18 joules, that's going to be equal to 1 calorie. And I want to take a little bit of time and define for you what a joule is. So there's some units that are hidden in here that you're familiar with. And I just want to give you a flavor for what measurements are in here. So let's do that. And I'm going to do that with some equations. You might remember the formula for kinetic energy, or maybe you've heard of kinetic energy before. A lot of people call this the energy of motion. It's not just the energy of motion, it's the energy of mass a little bit and motion as well. And so there's a formula for kinetic energy that you might remember. The kinetic energy of an object moving at a particular velocity or a particular speed is 1/2 the mass of the object times its velocity squared. And we're going to think of velocity as speed, how fast it's moving. And if we're going to use our regular metric units for this, here's our energy, our kinetic energy. That's going to be 1/2, which that's a number. It has no units associated with it. for mass, we're going to use kilograms. So let's see, mass is measured in kilograms. And speed, well, we can use meters per second for that. So I'm going to multiply this by meters per second. And of course, we've got to square that. So what that is a kilogram times a meter, which is a meter squared, divided by a second, because of the square here, per second squared. So the units of energy, according to this particular equation, are going to be a kilogram times a meter squared divided by a second squared. And this is what a joule is. This we give us this collection of units. A kilogram meter squared per second squared is a collection of units that we call a joule. And I can also show you this in terms of potential energy. There's an equation for potential energy, gravitational potential energy. If I want to know the gravitational potential energy of this piece of chalk on this table, that's about a meter above the floor. We'll pretend it's a meter, it's not quite. What is that? 91 centimeters it is, close enough to a meter. But nevertheless, if I want to know the gravitational potential energy that this has as a result of being up off the floor, the gravitational potential energy is just the mass of an object times the acceleration due to gravity times the height it is off the floor. Once again, if we look at the units of this, mass is measured in kilograms. Acceleration due to gravity is meters per second squared. And of course, heights are measured in meters. And if we look at this, once again, it has the units of kilograms times meter squared divided by second squared. It's an energy. Kilogram meter squared per second squared. And we remember that 1 kilogram meter squared per second squared is the same thing as a joule. It's identical to a joule. All right. I've been discussing conservation laws in this class a lot. You probably remember learning about the law of conservation of mass, which is important in balancing chemical reactions. You probably also remember the law of conservation of charge. We remember that if we start with a certain amount of charge in a chemical change, we need to end with the same amount of charge. There's also a law of conservation of energy. It says pretty much the same thing as the law of conservation of mass, it's just applied to energy rather than mass. And the law of conservation of energy says the amount of energy that we have in the universe is the amount of energy that we have in the universe. There's not going to be any energy magically appearing out of nothing, and there's not going to be any energy that's vanishing into nothingness. So the law of conservation of energy, or also known as the first law of thermodynamics, law of energy conservation, we'll say, the energy in the universe is a constant. The energy in the universe is a constant. And this may sound a little weird because you may have heard that, for example, we're running out of energy. Maybe you've heard that before. And it's important to remember when we're talking about energy changes that we need to think about not only the thing that's losing energy, but the stuff that surrounds the thing that's losing energy as well. And what the law of conservation of energy tells us is that if something is losing energy, something else must be gaining that energy. And if something's gaining some energy, well, that energy's got to be coming from somewhere. That's all the law of conservation of energy says. It's not, energy doesn't disappear, but it just goes from one place to another. And so when you're doing problems that deal with energy changes, which we call thermodynamics, and that's what we're going to be talking about a lot in this chapter, it's going to be very important for you to think about what is the thing that we're studying and what's surrounding the thing that we're studying as well. And usually in chemistry, the thing that we're studying is like a chemical equation. So I'm gonna write something pretty easy here. We're just gonna write H2O solid going to H2O liquid. And this would be, for example, we can imagine a piece of ice that's melting. And we would call this the system. The system is the thing that we're studying. The system might be my cell phone. It might be these glasses. You know, in chemistry, it's going to be the ice cube and the water, the liquid water that the ice cube has changed into. Or it might be some other reactants and products. But when we're dealing with thermodynamics, we have to think about both the system and the surroundings. And being able to do that is going to be helpful when you're thinking about the changes that occur in energy during chemical processes. So, one thing that we want to recognize as well is if we're dealing with just energy changes that occur when you're just physically putting a hot object and a cold object together. Let's say this. I've got a block of metal that's hot. So I'm putting temperature hot. And I have another block over here that I'm going to put TC. And that means its temperature is cold. It just means it's less than this. And the temperature here is higher than this. The way it works, the way the universe just happens to work, is if I take two objects at different temperatures, the energy is going to flow from the object at a higher temperature to the object at a lower temperature until their temperatures equalize. You don't get temperature running in the opposite direction. So you don't get a colder object transferring energy to a hotter object where this temperature goes up and this temperature goes down. That's not what we see. What we see is a flow of energy from the hot object to the cold object until the temperatures of both objects are equal. And we're going to use this sort of simple system to define a way that we talk about energy transfer, and the way we talk about those particular energy transfers, you can find that on slide 6 of the PowerPoint. We can talk about endothermic changes and exothermic changes. So endothermic and exothermic. In these terms, I see endo, which means into. It kind of sounds like into. And I see exo, which means outer or out of. Exo kind of sounds like exit as well. And I see the word therm in here, or at least the root word therm in here, that conjures up the idea of heat. And so in endothermic changes, what we're going to think of is energy as heat going into something. And the something that it's going into is going to be the system. And so when we have an endothermic change, we have energy as heat goes into what? Into the system, but it's got to come from somewhere. So where's that energy come from? It has to come from the surroundings. So in an endothermic change, energy as heat goes into the system, and it comes from the surroundings. And an exothermic change is going to be the opposite. Let me write that one up here. The opposite. So an exothermic change the exo refers to the system. The exo refers to the system. So in this case, energy as heat exits the system Notice, both Exo refers to the system. So exo, energy is heat, exits the system and goes into the surroundings. Okay, I'm going to give you a trick question now. See if you can catch it. Trick question. We're going to use these terms here, exo and endothermic. A log is burning and you're standing next to the log. Is that an exothermic change or an endothermic change? What do you think? It's a trick question. You really can't answer it. And the reason why you can't answer it is because I did not define what the system was. Are you the system? Or is the burning log the system? It's impossible for you to define exo or endothermic without clearly defining what the system is. So let's try the question again, and this time I'll clearly identify what the system is. You are standing next to a log that is burning. Are you going through an exothermic or an endothermic change? Well, if I'm standing next to a log that's burning, I'm getting warmer, and I'm the system. So if I'm getting warmer, energy is going into me. And if energy is going into me, that means I am going through an endothermic change. If I'm going through that endothermic change, something else must be losing energy. What do you think is losing the energy? The log is. As the log burns, it releases energy. So if we switch it around then and define the system as the log is going through an exothermic change as it releases energy, causing me to warm up. So whenever we're dealing with thermodynamics, it's going to be really important for us to remember we want to define the system, we want to define the surroundings, and we want to be able to think about things in that manner so that we don't end up confusing ourselves.